Alright, welcome back everybody. In this video we are going to talk about section 6.12 of AP Calculus BC, integrating using linear partial fractions. This video covers everything about partial fractions that you need to know for your AP exam, even though in this course we're going to do a little bit more with partial fractions. But the AP test only requires you to be able to use linear partial fractions of a non-repeating linear factor variety. So let's talk about this. Partial fraction decomposition is a technique that's used to break down a rational integrand that is difficult to integrate into the sum of two or more fractions, which are more easily integrable. We can do a partial fraction decomposition on p over x, p to the x over q, p of x over q of x. Sorry, my brain started misfiring there. We can only do that if the following two conditions are met. Both of these expressions are polynomials. Okay, so we can't use partial fractions if we've got natural log of x over a polynomial. And the degree of p of x has to be smaller than the degree of q of x. Now, that doesn't mean that we can't use partial fractions in situations where the degree of p of x is bigger than the degree of q of x. But if that's the case, we've got to do long division first, which we talked about a few sections ago. We would have to do long division, and then we'd end up with a remainder that required partial fractions, potentially. All right. In this lesson, we're going to focus on simple partial fractions. And so the factorization of our denominator is going to consist of non-repeating linear factors only. So let's take a look at what this looks like. I've actually outlined the steps of the process and shown going through this particular problem. So we want to, in this first example, we are going to integrate 5 over the quantity x squared plus 5x plus 6. The first thing we do, we find the factorization of the denominator. You see here I've factored x squared plus 5x plus 6. That's x plus 2 times the quantity x plus 3. Then we're going to write the decomposition by placing an unknown constant over each of these factors and taking the sum of these terms. So we're setting our original fraction here equal to a over the one factor plus b over the other factor. Okay? And then the way we solve for the constants is by multiplying this fraction by x plus 3 over x plus 3 and this fraction by x plus 2 over x plus 2, we've put both of these fractions over the common denominator, and that common denominator was our original denominator. So now all of these denominators are the same in this relationship. I usually don't show this step at any point in time in the process. But what does happen is, since the denominators of all of these are equal, that means the numerators of the left side and the right-hand side have to be equal to one another. So 5 has to be equal to a times the quantity x plus 3 plus b times the quantity x plus 2. Okay? Another way of thinking about this, if we distribute the a and the b through these parentheses, we get ax plus 3a on the right-hand side and bx plus 2b also on the right-hand side. And the left-hand side, there were no x's, but there was a 5. These two expressions need to be equal to one another. And this is how we're going to set up a system of equations in a partial fraction decomposition problem. There are no x's on the left-hand side. The number of x's on the left-hand side has to be equal to the number of x's on the right-hand side. The number of x's on the right-hand side is a plus b, which enables us to get this equation, a plus b equals 0. We do the same thing with the numbers. The numbers on the left-hand side add up to 5. The numbers on the right-hand side are plus 3a and plus 2b, and that leads us to this equation, that 3a plus 2b is equal to 5. This gives us a system of equations. We then solve this system of equations in order to get the constants that appear in these numerators way up here. So we solve that system, we get a equals 5, b equals negative 5. That enables us to write our original fraction as this instead. And so when I want to integrate the 5 over the quantity x squared plus 5x plus 6, we're going to replace that integrand with its partial fraction decomposition, which we see right here. And I'll tell you this from the experience, the hard part of partial fraction problems usually is actually finding those constants. Once we get those constants, the integrating itself, the calculus portion, is relatively simple. We can integrate this. It gives me 5 times the natural log of the absolute value of x plus 2 minus 5 times the natural log of the absolute value of x plus 3 plus a constant. We can simplify this using natural log properties. We could simplify this to 5 natural log of x plus 2 over x plus 3. Actually, I need an absolute value there. Plus c. So that's partial fraction decomposition and how it works. Let's go ahead and we'll work our way through a few examples doing this. All right, so the first thing I'm going to do in example 1, I want to integrate 2x minus 5 over x squared minus 7x plus 10. So I'm going to factor my numerator. X squared minus 7x plus 10 is equal to x minus 2 times x minus 5. So those are going to be my denominators in my partial fraction decomposition. And so this is equal to the integral of a over, and which factor I put first here doesn't matter as long as I'm consistent with which factor is paired with which constant as I solve here. Okay, so there's what we're trying to do. We're trying to break this down into this. Now, I'm going to multiply this fraction by x minus 5 over x minus 5, and this fraction by x minus 2 over x minus 2, but I'm only going to pay attention to the new numerators. I want those new numerators to be equal to 2x minus 5. And so I want a times the quantity x minus 5 plus b times the quantity x minus 2. That has to be equal to 2x minus 5. And so if I distributed through here, 2x minus 5 equals ax minus 5a plus bx minus 2b. I look at this, I've got x's, x's, x's. This enables me to write the equation that a plus b has to be equal to 2. And then numbers. Those enable me to write that negative 5a minus 2b is equal to negative 5. Now, once I have this system of equations, I can go ahead and solve the system of equations. I'm going to multiply this equation by 2. That gives me 2a plus 2b equals 4. So negative 3a equals, is that negative 1? So a equals 1/3. I substitute 1/3 back in here. B equals 5/3. And I check, that's negative 5/3, negative 10/3. Yep, those are correct. And so I can rewrite this original expression as the integral of 1/3 over x minus 2 plus 5/3 over x minus 5 dx. Now something else I'm going to want to do, since these are both divisible by 1/3, I'm going to go ahead and just factor a 1/3 out of this expression, because it's going to make this a little bit nicer for me to work with. Okay, and now that I'm here, I can just take the integral of this term by term. So I've got 1/3 times the quantity, natural log of the absolute value of x minus 2, plus 5 natural log of the absolute value of x minus 5. And I think I'm just going to leave that there for now. I'm not going to combine that into a single logarithm because I want to focus on calculus, not algebra. All right, there's my answer. But I could turn this into a single logarithm if I was doing, like, say, a multiple choice question that required me to match an answer. There's my integral. That's partial fractions. All right, let's look at example 2. First, we want to factor 2x squared minus 5x minus 3. Figure out what the factorization of that is. Let's see. I know I've got a 2x and an x, and I need minus 6x, so that's minus 3 and plus 1. And yep, there's my factorization. So this is equal to integral of a over 2x plus 1 plus b over x minus 3 with respect to x. I'm going to go ahead and do what I need to set up my system of equations. I've got 3x plus 5 has to be equal to a times the denominator of the other fraction plus b times the denominator of the first fraction, which means I can set up the system a plus 2b equals 3 and negative 3a plus b equals 5. Now I want to solve this system of equations. I'm going to go ahead and multiply this equation by 3. Gives me 3a plus 6b equals 9. Add these two together. Gives me 7b equals 14. So b equals 2. If b equals 2, a has to equal negative 1. All right, and so this is equal to the integral of negative 1 over 2x plus 1 plus 2 over x minus 3. And now I'm going to go ahead and integrate term by term. And this first one is a very common error for students. If I take the integral of this, you might think this is negative natural log of the absolute value of 2x plus 1. But if I took the derivative of this, it would be negative 1 over this expression times the derivative of the inside. Derivative of the inside is 2. So the derivative of this is actually twice what this fraction is. So I need to have a negative 1/2 in there. And then this one plays out straight. And there is the integral in example 2. And looking ahead, I don't think I have quite enough time to do example 3, unfortunately. If only I had an extra minute or two available of recording time, I could get through example 3. But we're going to cut this video off here, and we'll come back with one video where we go through example 3 to finish up this lesson on partial fractions. All right, hope to see you then. Have a great rest of your day, and enjoy yourself. Bye-bye.